Hello, everyone. We've got a really quick turnaround today. Sorry, I'm a little bit late. Just trying to. There's Ivan, the cat. Um, Very modest he is. Cleaning himself currently. Hi, Ivan. Ivan. All right. Gonna give him some privacy. Good morning. So I'm going to go ahead and get started since we don't have a lot of time. This lesson is going to be like 20 minutes, and then we'll spend the last 10 minutes in the Zoom room just to verify attendance, because I know some of you might forget to fill out the attendance form, so I will give you a chance to show your faces. Okay, so this week, the topic of this week is energy and the mass spring system. Okay, that's what we're going to be learning about this week. So let's suppose we have a mass spring system. Okay. So here's the spring, and here's the mass. Okay, and here is x equals 0. Okay, so when I say that this is x equals 0, I mean that's the equilibrium position. So that being the equilibrium position means that the spring is neither stretched nor compressed at this point. Okay. So now, and then I'm going to draw some stuff on either side just to help myself out. Okay. So what we're going to do is, let's imagine that the mass is pulled so that now it's out here. Okay. So it's pulled to this point, and it is released from rest. At that point. Okay. So what's going to happen, and I'm going to stop drawing the floor. I'm just going to draw it. So here's time 0. Okay, and I'm going to continue drawing this system at later times. Okay, now because the spring is stretched, it's going to pull the mass to the left, and so the mass is going to pick up speed. Okay, starts going to the left, and it's going to continue to pick up speed as it passes through equilibrium. Okay, so it's going really fast now. Okay. But then once it passes through equilibrium, now the spring isn't stretched. Now it starts to compress the spring. Okay. Now because the spring is being compressed, it's going to start to slow down. Okay. And then it's going to go to the other side, and it's going to be completely stopped. Okay, but the spring is still compressed, so it's going to now push the mass back to the right, and it's going to pass through equilibrium again. It's going to build up a lot of speed. Okay, and then the cycle just repeats. once we pass through equilibrium, now the spring is going to be stretched, and so it's going to start to slow down. Okay, so I've drawn a complete cycle of the mass going back and forth. Okay, now the first thing I want to talk about is this point at which the mass is furthest from equilibrium. That is called the amplitude. Okay, so the distance between the equilibrium position and the extreme point is the amplitude. Okay. All right. Now, and I wrote x equals plus amplitude because it is to the right of x equals 0. Okay. Now over here, when the spring is at maximum compression, okay, we're at x equals minus a. So the simple harmonic motion is motion between x equals plus a and x equals minus a, if the equilibrium position is 0. Okay? Bye-bye, Ivan. So let's think about the this moment right here in the motion. Okay? At this moment, it's released from rest. Okay? Because you just pulled the mass back and you let it go. Okay? So because it's released from rest, its velocity is 0. Okay? So when we think about the energy of this system, the energy is all going to be elastic potential. So it's going to be 1/2 kx squared. But the x value is 1 amplitude. So it's 1/2 ka squared is the energy at that moment. Okay? Now, so because it's stretched a distance a. Now, if we look at this moment right here, the spring is stretched, but not as much, and the mass is moving so that it has kinetic energy. So here we have the energy is elastic potential, where the x is whatever the x value of this coordinate is, plus kinetic energy. All right. Here we have, at this particular instant, we have x equals 0. Okay. Here we have x equals 0. Now, if x equals 0, the elastic potential energy it would be 1/2 times k times 0 squared. Okay. So what that means is that the energy is entirely kinetic energy. Okay. Now, because energy is conserved, if you have no potential energy, you are going to have lots of kinetic energy. Okay, the most kinetic energy that you have. So what that means is that the mass is going to be going as fast as it goes as it passes through equilibrium. So this is the maximum speed. Okay. At this particular instant, the spring is now partially compressed, and the mass is moving just not as fast as it was a moment ago. So we have that the energy is 1/2 kx squared plus 1/2 mv squared. Okay? Here, at the other side of the motion, the position is minus a, and the mass has no velocity at this instant. Why is that? Well, if it did have velocity, it would keep compressing the spring, and this is the leftmost extreme point. So the mass has got to be at rest here, just like it was at rest over here. And so we have that the energy is 1/2 k times negative a quantity squared, which is just a squared. Okay? And then it repeats. Okay, so then here we're going to have 1/2 k x squared plus 1/2 mv squared. Here we have energy is 1/2 mv max squared. Here we have both elastic and kinetic energy. All right. So now I'm going to flip the page, and we're going to do some observations about this. Okay. So let's do some observations about this discussion. Okay, so the first observation is that the total amount of energy in the mass spring system is equal to the amount of kinetic energy plus the amount of elastic potential energy. 1/2, I did it elastic plus kinetic, but okay. So the next observation is that the system has a constant energy. Okay? So the energy is conserved. Energy is conserved, but that energy is being exchanged between elastic potential energy and kinetic energy. Okay? So what that means, simple harmonic motion is an exchange between elastic potential energy, or potential energy in general, and kinetic energy. Okay? So basically what we have is we have all potential energy, some potential and some kinetic, all kinetic energy. So see how we exchanged, in going from here to here, we exchanged from elastic to kinetic, some elastic and some potential energy, all potential energy. So we've changed from all kinetic to all potential. Then some elastic and some potential, or some potential and some kinetic, all kinetic, some potential and some kinetic, all potential. So it just goes back and forth between potential and kinetic energies over and over and over and over again. Okay? So we're exchanging between those two to make simple harmonic motion. So the system has a constant energy, but that energy is being exchanged between elastic potential energy and kinetic energy over and over again. All right. So the system has its maximum kinetic energy. Okay. The system has its maximum kinetic energy as it passes through equilibrium. Okay. which in this case was x equals 0. So what that means is that it has this maximum kinetic energy as it passes through equilibrium. At that moment, it has no potential energy because the potential energy is 1/2 kx squared. Okay? So what that means is that we could write this energy as being all kinetic. And when it's all kinetic, you are at your maximum speed. Okay? The system has no kinetic energy at the extreme points. So when I say the extreme points, I mean as far right as it's going to go and as far left as it's going to go. So this will be x equals plus or minus a in this case. Now at the extreme points, because energy is conserved, if you have no kinetic energy, then you must have all potential energy. Okay? So if you have no kinetic energy at the extreme points, it has maximum elastic potential energy. Okay? So we could also write, if we evaluated the energy at the extreme point, okay, then we would have that the energy is 1/2 Ka squared. Now, all three of these expressions give the same number for the total amount of energy of the mass spring system. Okay? All three of these. But they're evaluating the energy at different points. So if we evaluate it at the extreme point, it's all elastic potential energy and no kinetic energy. So that's why there's only a 1/2 Ka squared and there's not a 1/2 mv squared. Okay? If you evaluate it at the equilibrium point, which it passes through equilibrium, then we have all kinetic energy and no potential. Okay? And if you're somewhere in between the equilibrium and an extreme point, you have both forms of energy. Okay? But because energy is conserved, all three of these are going to be equal to each other. You could set any two of them equal to each other that you want. So you could say 1/2 kx squared plus 1/2 mv squared equals 1/2 mv max squared. You could say 1/2 kx squared plus 1/2 mv squared equals 1/2 ka squared. You could say 1/2 ka squared equals 1/2 mv max squared. So these are all just comparing the energy at two different points. You see? All right. So this is just an introduction. We're going to go into greater depth on Friday. Okay, so I will see you in the Zoom room just to check in.